Alright folks, so this is a worked example video. We are going to discuss a couple of questions on the synthesis of amines, especially using the two important reactions that we learned, the characteristic reactions of synthesizing primary amines, which are Gabriel phthalimide synthesis and Hoffmann Bromamide degradation reactions. Okay, so let's look at the first question. It says, identify the products formed in this given reaction. Okay. So we have an ester, we are treating it with bromine in the presence of sodium methoxide. In the second step, we are treating it with potassium phthalimide, and the last step is an acidic hydrolysis. What is the product formed in this reaction? So let's solve this question step by step. Let's see what we get at the end of the first step. Okay. Now let's look at this ester. We have CH3, C double bond O, O, C2, H5. Correct? So what's the alpha carbon here? We know that this is the alpha carbon, CH3 is the alpha carbon, and this hydrogen attached to the alpha carbon becomes slightly acidic, and that's not new to us. We know that aldehydes and ketones also have acidic alpha hydrogen because of the electron withdrawing effect of the carbonyl group here. Now what happens when we treat this kind of an ester with sodium methoxide or like a strong base like ethoxide ion? Simple, it abstracts the alpha hydrogen. It abstracts an acidic hydrogen, right? So that's what exactly happens in the first step. In the first step of alpha bromination, in the presence of a strong base like ethoxide ion, it abstracts one of the alpha hydrogen atoms and gives us this anion. Now this anion is nucleophilic, right? It attacks the electrophilic bromine and gives us this alpha bromo ester. So this is what we get at the end of the first step. Now in the next step, we are treating this bromo ester with potassium phthalimide followed by an acidic hydrolysis. Now this is a classic Gabriel phthalimide synthesis, correct? So in the second step, a nucleophilic substitution reaction takes place where the phthalimide ion attacks and substitutes the bromine atom and gives us this N-alkyl phthalimide. In this case, because we have an ester group, its name would be something different, ethyl thalidoacetate, but that's not important. Names are not important here. All you need to look at is what is happening, correct? So an SN2 reaction takes place. It displaces the bromine atom and gives us the substituted product. And what's the last step? Last step is an acidic hydrolysis, right? And we know that in acidic hydrolysis, or for that matter, even in basic hydrolysis, this ring opens up and releases a primary amine. So the last step is an acidic hydrolysis where the ring opens up, gives us phthalic acid and corresponding primary amine, right? So this is the primary amine that we got here. So is that right? Is this our final product? If you think the answer is yes, then I would urge you to think again. What is happening in this reaction? This is an acidic hydrolysis. And what do we have here? We have an ester linkage, right? Esters easily undergo hydrolysis in acidic medium. And what are the products of ester hydrolysis? We get an acid and corresponding alcohol. So in the last step of acidic hydrolysis, along with phthalic acid, a primary amine, because it has an ester linkage, would undergo hydrolysis further. So basically the final products obtained in this reaction would be phthalic acid, yes, it's the same here, and the ester hydrolysis products, which are NH2CH2COOH and ethanol, CH3CH2OH. So this primary amine is actually an amino acid glycine, and these are the different products that we get at the end of this reaction. So let's look at one more question. So let's look at the next question. It says, how can we convert benzene to aniline using Hoffmann Bromamide degradation reaction? So let's simplify and say Hoffmann rearrangement. Okay. So for that, this is the conversion. We need to get aniline from benzene, and we have to get this by using this rearrangement reaction. And how do we do this? So let's go back and recall what exactly happens in Hoffmann rearrangement. We get a primary amine from an amide, right? So where's the amide here? So basically we need to do this. We have to convert a benzene first to benzamide and then employ Hoffmann rearrangement to get aniline. So that is how we need to go ahead. We have to break this reaction into two parts. First, how to get benzamide from benzene, and second, how to get aniline from this amide. So how do we get benzamide from benzene? Well, we know that benzamide or any amide is a derivative of the corresponding carboxylic acid. So the carboxylic acid in this case is benzoic acid. So when we treat benzoic acid with ammonia, we get benzamide. And how do we get benzoic acid from benzene? Okay, by oxidizing toluene. You see, benzene can be easily converted to toluene by using Friedel-Crafts alkylation reaction. And this toluene, the alkyl group, can be easily converted to benzoic acid by using a strong oxidizing agent, alkaline KMnO4. Now these are things that you've already learned. We are simply doing a recall in this video. So benzene to benzoic acid can be attained through a Friedel-Crafts reaction followed by oxidation, and benzoic acid to benzamide by simply treating it with ammonia. So we have achieved the first step. The second step is simply converting benzamide to aniline, right? And that we can get by using Hoffmann Bromamide reaction, which is to treat this amide with bromine in the presence of a strong base to get corresponding amine. And to quickly recall what happens in this reaction, the first step is the deprotonation step followed by nucleophilic attack. In other words, we get N-bromobenzamide. And the second step is again a deprotonation step where we lose this hydrogen atom and we get a negative charge. And the rearrangement takes place here. Phenyl group moves towards nitrogen, a double bond forms here, and bromine gets eliminated, right? So with the elimination of bromide ion, we get an isocyanate here. Now here again the OH minus attacks the carbonyl carbon and gives us this corresponding carbamic acid, which again being highly unstable immediately loses this part as carbon dioxide, giving us aniline as the final product. So this is the mechanism. If you have any doubts in this mechanism, I would recommend to revisit the video on the mechanism of this reaction. We are right now simply solving questions, so I wouldn't want to dive deep into what is happening here. Okay, so if you have a doubt, please do go back and look at the mechanism of this reaction video. Okay, so that is how we get aniline from benzamide by using Hoffmann rearrangement reaction. Now remember, this is not the best way at all to achieve this conversion from benzene to aniline. In fact, the best way to achieve this conversion is to simply nitrate benzene, where we get a nitrobenzene, and then perform a reduction reaction using FeHCl to get aniline. As you can see, it has only 2 steps, and this is the most efficient way of synthesizing aniline from benzene. Now remember, the reason we went through so many steps from benzene to aniline, that is first convert to benzoic acid, then benzamide, and then aniline, was to incorporate this step. To remind you that for Hoffmann rearrangement to take place, we have to have an amide as a starting reactant. So to get aniline using this method, we must begin with benzamide, and whatever reaction gets us to benzamide. So let's look at one more question before wrapping up this video. So the last question says, which among the following will not undergo Hoffmann bromamide degradation reaction? So we need to see which among them will not undergo this rearrangement and give us the corresponding primary amine. Okay, so to solve this question, let's look at each compound one by one. The first one is PHCONHBr. So if you look at this compound closely, you will see that this is nothing but N-bromoamide, right? Which has the formula R C double bond O NH Br, isn't it? So this is N-bromoamide, and here R is replaced by phenyl group, and we get this when we treat an amide. The amide, corresponding amide, would be PHCONH2 benzamide, right? And when we treat benzamide with a base followed by its reaction with bromine, we can see that OH minus would abstract this acidic hydrogen from this, and nitrogen would attack the bromine and give us this particular intermediate where R is nothing but pH group. Correct? So this is already a part of the Hoffmann reaction. PHCONHBr is formed when benzamide undergoes Hoffmann bromamide reaction. Correct? So that means this will undergo Hoffmann reaction and give us aniline as the final product. Now what we have here is again PHCONH2 benzamide, and we know that benzamide is a primary amide and it will undergo Hoffmann rearrangement reactions. So this will undergo the reaction as well. Now let's look at the third option. We have PHCONHCH3. Now this one is tricky because this is a secondary amide. Here the nitrogen is bonded to a hydrogen atom and a methyl group. So this is a secondary amide. Now secondary amides do not participate in Hoffmann rearrangement reaction, because if you look at the mechanism, you will see that in the second step of deprotonation, we need another hydrogen atom attached to this in order for the isocyanate intermediate to form. So if this particular secondary amide underwent Hoffmann reaction, what do you think would happen? In the first step, we have the OH minus that will abstract this particular hydrogen atom and give us a negative charge here. It will react with bromine and give us the corresponding N-bromoamide, right? So in this case, we would get PHCO NBrCH3. Now the second step is again another deprotonation. The hydroxide needs to abstract one more hydrogen atom so that the bromine can leave and the rearrangement can take place. But you can see that here there is no second hydrogen atom attached. So that means this second deprotonation will not take place, and as a result, the secondary amides will not be able to undergo Hoffmann rearrangement reaction. So this one will not undergo the reaction. What about the last one? Well, this is straightforward, right? This is acetamide. This is again a primary amide, and primary amides would undergo Hoffmann reaction, and the product obtained in this case would be methylamine, CH3NH2. Correct? Alright folks, that's it. We get amazing and super interesting questions on these reactions, so make sure that you understand the mechanism well of both of these reactions. Okay? So see you all in another video.